Hello and welcome to Lecture 10 of Math 2R03. In today's lecture, we are going to be looking at Section 3B of the textbook, where we're going to learn about null spaces and the range. And just to kind of give you a quick recap of where we are, last time I introduced the space of all linear maps between vector spaces V and W. So we have a collection of functions between V and W, and we saw that last time that this set is also a vector space. Now what we're going to do today is look a little bit more closely to the elements that belong to this vector space. And what we're going to show is that each element T inside of this vector space is going to give us subspaces of V and W. Okay, so we're going to show that T defines subspaces of V and W. Okay, so that's kind of our goal today. And these subspaces will be the null space and the range. Okay, so the first thing that we're going to do today is look at the null space. And here's the definition. I'll finish filling it in as we go along. So take some element in this vector space. So this is just a linear map from V to W, the null space of T, and depending upon some books that you're looking at, they may call it the kernel of T, denoted null T, is all things inside of V such that when you plug them into your function, T, they get mapped to 0 in W. And so each of our elements belong to V, so this is a subset of the vector space V. Okay? And now this is called the null space, and one way to think of the null space is that it's all things in V that are sent to 0 in W by the linear map T. So let me give you a couple examples of the null space. Okay, so we always know that the 0 map belongs inside of this set of linear maps from V to W. So let's look at the 0 map. Okay, so i.e. this is the map where TV equals 0 for all V in V. Okay, but now if you look at the definition, the null space contains every V that T maps to 0, but in the 0 map, everything gets mapped to 0. So in this case, what we have is that the null space of T is all of your vector space V. Okay, so this is give you one example of a null space. Okay, what about another example? Okay, so here's an interesting function. We haven't done too many of these yet. Here we're looking at the vector space F infinity, and we're looking at linear maps from F infinity to F infinity. So remember that these are like infinite sequences, A1, A2, and so on, and we're mapping it to a new infinite sequence. And so the way that this map that we're looking at is it takes an infinite sequence, A1, A2, and so on, and what it does is it kind of truncates the A1, it removes the A1 and then basically moves all the elements over. Okay, so A2 now becomes the first one, A3 becomes the second one, A4 becomes the third one, and so on. So chop off the first element and then kind of shift everything to the right. So the question is, what is in the null space of this linear transformation? Well, we want all of these things here to be 0 at the end. But the A1, it could be anything that we want, right? Because when we apply the operator T, it kind of chops off the first element. So it turns out that the null space is all sequences that look like A and then all zeros afterwards. Oops, there's no last one. Here, let me make this a little bit clearer. Where A could be any arbitrary element of F. So I can take any sequence that has anything as my first element, zeros everywhere else. I stick it into my function and I will get the sequence of all zeros. So that's what my null space looks like in this case. And it's definitely not all of F infinity, right? So this is strictly contained inside of F infinity. What about another example? Okay, and so this example is kind of interesting because we see a connection to math 1B03. So here we have a linear transformation going from F3 to F2, and if you would like, you can think of this as R3 and R2, and it takes a tuple or a triple, x1, x2, x3, and it uses those and it into F2, where the first coordinate is x1 plus 2x2 plus 3x3, and the second coordinate is 2x1 plus 4x2 plus 6x3. So the null space of this transformation would be, if we just look at the definition, it's all elements x1, x2, x3 inside of F3, and we need this guy, the first coordinate, to be 0, and we need the second coordinate to be 0, right? So we require that x1 plus 2x2 plus 3x3 is equal to 0, and we require that 2x1 plus 4x2 plus 6x3 is also 0, because we want this coordinate and this coordinate to go to 0. Okay, but if you look at what I've written here on the right-hand side, right, this is a system of linear equations. So we're back in the land of Math 1B03. And we actually learned a lot in Math 1B03 is that we can actually find a spanning set. We can describe all solutions. Because in some ways this description is not very useful, because I can't really tell if the vector you give me belongs to this set or not. Right? So how can we kind of describe all solutions? Well, this system of linear equations, okay, so this system of linear equations, we can rewrite it in matrix form, and so let me do that. It looks like the matrix 1, 2, 3, 2, 4, 6 times the vector x1, x2, x3, and we want this equal to the vector 0, 0, 0. Oh, sorry, there's too many zeros there. Fix that up. And now we can use linear algebra, right, by looking at the augmented matrix 1, 2, 3, 0, 2, 4, 6, 0, and we can row reduce it. And I picked a nice example, so it's very easy to row reduce. So we get 0, 0, 0, 0. And remember, then we have to count the number of free variables, right? So x2 and x3 are free variables. And we see that x1 has to satisfy minus 2x2 minus 3x3. If I went a little too fast here, I suggest that you go grab your linear algebra book from first semester, from your first course, and kind of review what I just did. And to finish up this problem, all right, what we have then, because x2 and x3 is free, and x1 is written in x2 and x3, all of my solutions look like x1 is negative 2x2 minus 3x3. The x2 is free, so I put an x2. x3 is free, so I put an x3, 3. And then I take the arbitrary solution and I factor out the free variable x2, and I factor out the free variable x3. So I have x2 times the vector minus 2, 1, 0. And I have the vector x3 times the vector minus 3, 0, 1. So that the null space, putting all the pieces together, is the span of the vector minus 2, 1, 0, minus 3, 0, 1. So all linear combinations of these vectors gives me the null space of T. Okay, so here what we're seeing is stuff that you did in Math 1B03, which is finding all the solution. Oops, excuse me, let me fix that. Finding all solutions to this homogeneous system of equations is really finding the null space of a linear transformation. So that's kind of the connection here. Maybe I'll make that kind of explicit, is that, so 1B3 connection, if A is m by n, then the null space of your matrix A corresponds to the null space of the linear map, which is given by Tx is equal to A times x. So we're just kind of connecting things up in this lecture part here. So in the next part, we'll say a little bit more about the null space of a linear transformation.